So yesterday we talked about all the rules for basic integration. And like I said, those are all the rules there are. It's not like I'm going to spring any more basic rules on you. So any questions about any of that stuff?
Can you say there's like something about the chain rule?
Yeah, there's a little technique that we'll learn that has something to do with the chain rule, but it's based on these basic rules. Okay. So today we're going to do something that's really important in the scheme of things. It's called the fundamental theorem of calculus. Okay, so that's what we're going to talk about today, the fundamental theorem of calculus. Calculus doesn't start with an F. And today we're just going to talk about part one of that theorem. It's a two-part theorem, and we're not going to talk about the second part of the theorem for a few weeks. Okay, so the fundamental theorem of calculus, part one. This is abbreviated. You can abbreviate it anytime you refer to it as just FTC. Okay, so we have IVT, EVT, MVT, Rolle's theorem, and now FTC. Okay, those are the special theorems that we've talked about so far. So what FTC part one is it's basically like a recipe of how to calculate definite integrals. Okay, so this is just FTC part one is a recipe. I don't know what else to call it, for calculating definite integrals. Now, what definite integrals are and what they're for, we're going to hold that off until later. Okay, for now, we're just going to think of it as like a computation that we're doing. It's like when you first learned how to add numbers, for example, you didn't really know all the applications that would entail, right? Like all the things that would be good for. Same thing here. You're not going to know all the things that definite integrals are good for, and there's a lot of them until later, but that doesn't mean we can't learn how to do the process, okay? So try not to get too hung up on like what exactly is this, and just instead focus on the process of like what we're doing instead of why we're doing it. You understand what I mean? Because I think it would be much more confusing to first talk about all the ways this is going to be used and then do it. I think it would be more time consuming and less clear that way. Okay, so here's the rule, or here's the FTC part one. It's if capital F of X is any antiderivative of little f of x. So remember, antiderivative, that's just code word for indefinite integral, right? That's what we've been doing the last couple of days, is taking antiderivatives, which are really integrals, indefinite integrals. So f of x is any antiderivative of f of x. And when I say any antiderivative of f of x, that means c can be any value, right? Normally we have, like if we're integrating x squared, the answer is x cubed over 3 plus c. So this is just saying it could be any one of those c values. It could be, c could be 1, or c could be negative pi over 2, or whatever. C could be any constant. Then the symbol for definite integrals is an integral symbol with a number on the bottom and a number on the top. Of f of x dx. is equal to capital F of x, and this is the way it's written, capital F of x with a vertical line after it, and then a and b. And remember that vertical line, we've seen that vertical line before when we were evaluating derivatives. Remember, the notation then was, I'm going to write it in chalk over here just so that I don't mess up my notes, but the notation then was something like the derivative of, or maybe like df dx evaluated at x equals 3 or something like that. That vertical line meant evaluated at. Or we maybe took a, for example, an implicit derivative, right? So we took an implicit derivative, and it was like dx of like an implicit function like x squared plus y squared equals 4, evaluated at, and then we had like an x value and a y value, so like 1 radical 3 or something like that. This was the derivative of this implicit function, which is really just a circle, evaluated at that point which lies on that implicit function. Do you remember this notation? Okay, so that's the same thing. This is evaluated from A to B. This is an interval of x values. A and B is an interval of x values. And then this just means f of b, capital F of b, minus capital F of a. That's it. That's FTC part 1. It's just saying to evaluate a definite integral, you take an antiderivative, you substitute in b, and you substitute in a, and you subtract them. That's it. Okay? There's really nothing more to it. So if I have something like the integral from 2 to 3, and notice how I'm saying from 2 to 3, but I'm writing the 2 on the bottom. It's kind of like, think of like when you do like summation notation, like the big capital sigma, the smaller number goes on the bottom and the bigger number goes on the top. Kind of the same way here. It doesn't have to be smaller number, bigger number, but that's the way it is often, okay? So if I have this of x squared dx, this is just going to be x cubed over 3 evaluated from 2 to 3. Now I said up here it could be any antiderivative, so why not just pick the one where c is 0? Wouldn't that be the easiest one to pick? Yeah, of course. So then this is just going to be 27 thirds minus 8 thirds. So the answer would be 19 thirds. Now notice, if I had picked a different antiderivative, I would get the same answer, right? Like if I picked, instead of x cubed over 3, suppose I picked x cubed over 3 minus 7 and evaluated that from 2 to 3. That would mean the answer would be 27 thirds minus 7 minus 8 thirds minus 7. Don't you agree that you're going to get the same answer? Because the c's are going to cancel each other out, right? So save yourself a little bit of a headache and just always pick the antiderivative where c is 0. It's just making yourself have less work. Everybody clear with that process so far? So let's just do a few examples, and then I'll show you that your calculator actually does this for you also. So what if you have something like the integral from 1 to 4 of dx over the square root of 9x cubed. So this would be good practice for actually taking indefinite integrals as well. The first thing I would do is I would rewrite this as the integral from 1 to 4 of 1/3 x to the negative 3/2 dx. Everybody cool with that? I just rewrote the radical as power. And then this ends up being 1/3 x to the, if I add 1, I get negative 1/2 divided by negative 1/2, which is times negative 2. It looks like that, right? Kind of. evaluated from 1 to 4. So this is like -2 over 3 radical 4 minus -2 over 3 radical 1. I'm plugging in 4, and then I'm plugging in 1, and I'm subtracting the 2. So this ends up being -1/3 plus 2/3. The answer is 1/3. So it's just a computational technique. That's all FTC is, part 1. It's just a computational technique. It's how do you do this thing? So you just take the indefinite integral, plug in some numbers, and subtract. Is anybody confused, or does everybody understand what I'm doing? Not too bad, right? Let's try one that's a little bit harder. What if I had something like the integral from -1 to 1 of x cubed plus 2 squared? What would I have to do here?
Question.
Yeah, sure.
So for the one above it, because you said we don't usually have to simplify stuff, if we were to just leave it as that.
You could leave it like this. You can't leave it like this,
Right, okay.
right? So if you're gonna not simplify it, it's perfectly fine. You would get full credit for this, but you wouldn't get full credit for this. It's just like, no, it's not like that. I was gonna say, it's like if you have a trig function, you don't evaluate it. That's okay though. You're allowed to leave like sine pi over 2 and leave it just like that. So that's not the same thing. Never mind.
For this one, you boil it out, right?
Yeah, this one, there's no chain rule, so you have no choice. You have to FOIL this out, right? So this would be the integral from -1 to 1 of x to the 6th plus 4x cubed plus 4 dx, which would be x to the 7th over 7 plus 4x to the 4th over 4 plus 4x, evaluated from -1 to 1. Those 4's cancel, so let's see, that makes that a little easier. And again, I'm going to take Bella's advice and not simplify this whole thing, but it's going to be 1/7 plus 1 plus 4 minus -1/7 plus 1 minus 4. Okay? You can kind of imagine that there's a lot of places to make little sign errors and things like that, so you got to be really careful when you're doing definite integral. Yeah?
So you said that you don't have to put the small number on the bottom necessarily, but if you don't, then you have to.
You'll get a different answer. Yeah, like, how will the answers differ? Let's think about it. Yeah, what did you say?
It'd be opposite sign.
Yeah, it'll be the exact same answer, but opposite sign. Yeah, so like up here, if this was the integral from 4 to 1, I'm just going to take this term and subtract it from that term, which is going to give me the negative answer. If you subtract things in a different order, you get the negative, but the same absolute value. That's exactly what's going to happen here. Okay. Let's try another one. How would you do this one? The integral from 1 to 3 of 3t minus 5 over t to the 4th dt.
Could you just go back up a little?
Yeah, sure. Try not to get confused by different variables. It doesn't matter, right? As long as the variable in the integrand matches the variable on the d, you're good. It's the same exact process, but your answer is going to have t's in instead of x's. It's just like when you're differentiating a function of theta, you're going to end up with thetas in your answer. That's all. Yeah.
So you do t to the -4, and then don't you distribute it?
Yeah, that's one way to think of it. You could do t, think of this as t to the -4 and multiply it in, or you can just think of this as like two separate fractions, like this fraction and this fraction, which is really kind of the same thing as what you said, right? So this is just going to be the integral from 1 to 3 of 3t to the -3 minus 5t to the -4. And then the rest of it's pretty clear, right? I'm just trying to give you some ideas of how they might try and fool you into like doing the wrong thing. There's no quotient rule. You don't just integrate the top and integrate the bottom or something like that. That definitely doesn't work. So this wouldn't work if this was the reciprocal fraction, we would have no way of taking its integral. Like if this was t to the 4th over 3t minus 5, you can't split that up into two fractions, right? Everyone know what I'm saying? So if the denominator is one term, you could split it up into two fractions, but if the denominator is multiple terms, you can't do that.
But that doesn't mean that there's no derivative that exists that doesn't have that.
It means that using our elementary methods that we know, you can't do it yet. Yeah. Maybe that kind of chain rule trick might work in some situations like that, and maybe it won't, but I just know that I can't do this to it. How about this? What if I have the integral from 0 to pi over 3 of sine 3x? So the integral of sine 3x would be negative cosine 3x over 3, right? The integral of sine is negative cosine from 0 to pi over 3. So it's the same thing, right? This is just going to be negative cosine of 3 times pi over 3 minus negative cosine of 3 times 0 over 3. And then I can evaluate this. This is, I'll actually do this one. So this is negative cosine pi. What's the cosine of pi? It's -1, so negative cosine pi would be positive 1/3. What's the cosine of 0? 1, so the negatives cancel, you get 1/3 plus 1/3. The answer would be 2/3. Okay. Let's just do 2 more examples. How about the integral from ln2 to 3 of 5e to the x? What's the integral of 5e to the x? 5e to the x. ln2 to 3. So this just means it's going to be 5e cubed minus 5e to the ln2. If this was a multiple choice question, how would the answer look? Yeah, it would be 5e cubed minus 10. That's exactly what you would see. Does that make sense? Because e to the ln2 is really just 2. This whole thing is really just 2. Okay, one more example, and then I'll show you how to use your calculator for this. How about the integral from 1/2 to 1 of 1 over 2x? Yes. What's the integral of 1 over 2x?
X to x squared.
1/2 ln of x, not ln 2x. It's 1/2, because the 1/2 is a constant multiple. The integral of 1 over x is ln x, right? So this is 1/2 ln x from 1/2 to 1. Does that make sense? So you can't forget that special little exception to the power rule. So this is 1/2 ln 1 minus 1/2 ln 1/2. Now, if this was multiple choice, there's lots of ways, lots of things they can do to try and trick you. ln1 is 0, right? So this whole thing is just going to go away. But here you have negative 1/2 ln of 1/2. Think about all the ways they could manipulate this to try and confuse you in a multiple choice question. They could write this as negative 1/2 of ln1 minus ln2, right? That's a rule, right? The quotient rule that deals with logs. And then this is also 0, ln1 is 0. So this is negative 1/2 times negative ln2. But they might write that by canceling the negatives and writing this as a power. They might write this as ln radical 2. Like that might be the answer that's in the multiple choice. And you might not recognize it immediately from this. You got to think about how they might try and hide it, you know? That's like someone's job to like, how can I fool these youngsters? All right, that's what I'm going to do when I retire. I'm going to sit in a room and do calculus and drink a lot. And maybe golf if I have time. All right, so that's the process. Any questions on the process? All right, so let me show you how your calculator can be used to do this. Your calculator will evaluate definite integrals. So using the TI 84 plus, and I know you might not have them today, that's okay. That's why I'm just writing down the directions. There's two ways you could do this, okay? The first way number one, is you just press Math 9, the Math button, and then number 9, okay? So like, for example, suppose I wanted to do, let's do one that we've already done just to save a little time. So let's say I wanted to do the first one, the integral from 2 to 3 of x squared. That's the example I'm going to use. The integral from 2 to 3 of x squared dx, and the answer was 19/3, right? So if I wanted to do that on my calculator, this is TI 84 plus, I got a newer version of it, so it's just like what your calculators look like now. I just pressed Math, maybe? There it is. And if you scroll down, you can either press the number 9, or if you scroll down, you see there's more choices. Math 8 is numerical derivative. Math 9 is integral of a function integration. So you press enter, and it gives you a little definite integral symbol. So if I wanted to integrate from 2 to 3, I press 2, the up arrow, 3, right arrow to get into the parentheses, x squared dx. You have to type in the variable you're working with, and it gives you the answer. 19/3 is the answer that we got, and that's 19/3. Okay, so that's one way to do it. You just press Math 9, and then you just fill in the blanks where they go. This is much easier than the way it used to be. It used to be that you had like a whole syntax. Like you had to do fn int, and then type in the function, and then do a comma x, comma a, comma b. It was like a total like mess. So this is nice because it looks exactly like it looks on your paper.
Yeah, it's crazy to think about how that's like coded.
Yeah, I don't even get how they do this.
Yeah,
it's crazy.
It's weird.
So that's the first way, Math 9. Now, as always, if you have a function that's already in your y1 or y2, like say I had a function that was really complicated that I had already typed in, and I don't want to type it in again, right? I could just refer to y1. All I would do is from the main working screen, I'd press Math 9, the integral from 2 to 3, and instead of typing in the function like the whole thing, I could just say y1, which remember that's variables, y variables, function y1 dx. So now this is just going to integrate whatever I have already typed in to y1. And you're going to have problems for sure that, like a free response question where you do lots of stuff with it, you want to just type it in one time and be really careful that you don't make any mistakes with parentheses or anything like that. And then you never have to type it in again. You can always just call it y1. So if I do this, it gives me the same answer because it's referring to the same function. Okay, so that's the first way to do it. The second way to do it is from the graph of the function. Way number 2 is from the graph. Okay, so if I wanted to graph this function, it's super easy. I could I just type it in and then press graph, x squared, right? And then I would just press second calculate, so second F4, second F4, which is calculate. And then one of the choices, remember that was the same place we went to find value, 0, and intersection, and maximum. The 7th choice down here is integral. So I could just press 7. Press 7. And it's going to ask me for the lower limit and the upper limit. In other words, what number is at the bottom of the integral sign and what number is at the top of the integral sign. So if I press 2, then 3, then enter, it gives me the same answer. It does a little shading on the graph. Don't worry about what that shading means for now. I'll explain it later, but the answer is still the same. Okay, so it's second calc, choice 7. And then you'll have to enter the lower and upper limits. Those numbers are called the limits of integration. The lower limit, the upper limit. Okay? Then enter A and B. Okay, so there's 2 different ways your calculator will evaluate definite integrals. Okay? So what I want you to do on this Delta Math assignment, this Delta Math assignment is called just FTC Part 1, is do the definite integrals by hand, and then just verify your answer using your calculator. Don't do it all on your calculator, because then you're not going to get the practice of actually doing the process. And remember, more than 50% of the test is non-calculator, like the AP exam. So you got to know how to do it both ways. But that way, this way, you'll get practice doing it by hand, and then you'll get practice. You get really good at doing it on your calculator. So do it by hand, check it, then submit your answer. Do it by hand, check it, and then submit your answer. Any questions? I'm gonna stop recording.
So,